Okay. So in the projections, we have dealt with two types of projections we use commonly to represent molecules. The Fisher's projection as well as the wedge dash projection. The Newman's projection we will take up today. In fact, in your BScs, you have learned about conformations. Is it not particularly about conformations of alkanes and cycloalkanes? When we write the conformation of molecules like ethane, we come across different conformations of ethane like staggered, eclipsed, and when it comes to butane, gauche. These are the different conformations we come across. And if you can remember, we used to represent the conformations using a particular type of formula called Newman's projection. Is it not? So what is Newman's projection? Newman's projection is drawn after viewing the molecule from the front. What do we mean by front? See, this is the picture of ethane. I have constructed ethane molecule here. Now, the angle of viewing is here. Okay. The angle of viewing is here. That means you are looking at the molecule, holding the molecule in such a way that the carbon, 3 hydrogens are in front of you. It's like holding a flower, okay, with its stalk, flower with its stalk in your hand, and the petals facing towards you. In that, I mean, I told you, right? Projection is nothing but writing the 3-dimensional structure on a 2-dimensional paper by looking at molecule from different angles. For wedge dash, we looked at a molecule from one angle. For fissure, in the other angle. In the Newman's, this is the angle. How would you see the molecule then if you look at the molecule from this point of view? This is how you see the molecule. Can you see a big sphere here? That would be the carbon. Where is the other carbon? And that other carbon is eclipsed by this carbon, is it not? Can you see the other carbon which is behind you? No, definitely not, because all the sizes of the atoms are similar. So this carbon is almost eclipsing. The front carbon is eclipsing the rear carbon from the viewpoint. See, this is only as you see. It doesn't mean the molecule has single carbon. It has 2 carbons. But 1 carbon is visible to you from this angle of viewing. Okay. It's like almost your solar and lunar eclipse. Yeah. When in solar eclipse, you have moon in front of you and moon eclipses your sun. Does it mean the sun is not there during the eclipse? It is there. You are not visible to you because it's the angle of, it is the point on the earth you are standing in such a way that the moon is eclipsing your sun. Okay, not your sun, our sun, everybody's sun. Okay, fine. It's like this. Now, where are the hydrogens now? You can see the hydrogens in the green color here, green hydrogens towards you. Is it not? And what are these pink hydrogens? Away from you. So to demarcate this structure, we will use terms like front carbon and rear carbon. Rear carbon, not R-A-R-E, rare. Rare andre aprupa, not R-A-R-E, R-E-A-R, rear carbon. That means backside, behind carbon. Rear carbon. The rear carbon is not seen in the projection. The rare hydrogens can be seen depending on the conformation, whether it is eclipsed or staggered. If it is eclipsed, again, these hydrogens eclipse these hydrogens, you cannot see. Staggered, you can see. Now, staggered conformation of the molecule I have written here. The front carbon is represented here with a sphere and an eclipsed rear carbon. 3 hydrogens attached to the rear carbon, 3 hydrogens attached to the front carbon. Okay. And of course, this is the ball and stick model you are viewing. But how to convert that into a structural formula? In the sense, how to convert that into a formula? Writing down purpose. You see this. In the Newman's projection, the front carbon is represented by a dot. The back carbon is, or the rear carbon or the back carbon is represented by a circle. Fine. Written behind that dot, circle. And the atoms attached to the front carbon, as usual, you connect them through bonds, and the atoms attached to the atoms or groups attached to the rare carbon, as usual, you connect them by bonds again. Okay, so this becomes the Newman's projection of ethane molecule. Of course, why the Newman's projection is used, where is it used too much? It is used in conformational analysis of the molecules. I hope you understand the meaning of, I hope you remember the meaning of conformational analysis. Anyways, so to depict different conformations, this is the best projection. And if you can recall, what is this projection? What is this conformation? The name of this conformation in which I have presented the ethane? What is it? Somebody can answer this. Somebody can answer this. What? Is it eclipsed or staggered?
Staggered.
Staggered. Okay. In the eclipsed conformation, if you want to write, you are not going to see the rare hydrogens, is it not? They are getting eclipsed by the front hydrogens. Strictly speaking, they are getting eclipsed by the front hydrogens. See this? The molecule represented with ball and stick, I have converted that into Newman's projection. The front hydrogens pink or red, the back hydrogens white. The front carbon with a dot here and the back carbon with a circle there. Okay, fine. So this is how Newman's projection of a molecule is written. Okay, fine, no problem. This is all how we did it. Fine. Can you see now? I have dissected the formula into different components. First, you write a dot with 3 bonds, and then you write a circle with 3 bonds. You coincide or overlap the dot with the circle. That means front carbon with the back carbon. Fine. Now, that was for ethane. Now look at the Newman's projection of butane, CH3. Okay. If I say the Newman's projection of butane is like this, actually, how many carbons are written with the symbol C in this projection? How many carbons are written with symbol C?
4.
No. 4 carbons in total in butane. But how many carbons are written as C?
2.
2. Where are the remaining 2?
2.
Where are the remaining 2?
One dot.
One dot, okay.
One circle.
Super. Correct. Very good. The dot, the circle, and the methyl group. Actually speaking, if you have to number this, how do you number this? Which one gets the first numbering? Does your dot get?
No, sir.
No. The methyl group gets first. This is the first carbon, second carbon, circle is the third carbon, this is the fourth carbon. Is it not? So, in alkanes particularly, the conformation is written taking into consideration the middle carbons, not the terminal carbon. Terminal carbon is usually shown as a substituent. The middle carbons are made dot and circle. Okay, please remember. So again, this is the staggered conformation of butane, eclipsed conformation of butane. And you know, conformational analysis itself is a separate and a big topic in stereochemistry, which we are not going to do now. But as of now, you just understand how to write the Newman's projection of compounds. And Newman's projection is best used for writing down the conformations of alkanes and even cycloalkanes. The chair and board conformations, you can write Newman's projections. Now, you see this. How we have, okay, anyway, we will take up this when we write interconversions. Just we'll do interconversions. Sawhorse projection. This is the last type of projection we are going to study. Sawhorse projection. Sawhorse projection is nothing but Newman's projection viewed in a tilted angle. Okay, Newman's projection viewed in a tilted angle. In Newman's projection, if this is the molecule again, our butane, you are going to view from this point exactly where the front carbon is coming in line with your eyesight. Is it not? The front carbon is coming in line with your eyesight. This is the angle of viewing in the Newman's projection. In the Sawhorse projection, what we do is we will tilt this molecule a bit. So instead of keeping our eye in this line, we will keep our eye here. So in Newman's projection, we are viewing the molecule up front, whereas in Sawhorse projection, we are viewing the molecule sideways. Please remember, sideways. What do we mean by this sideways? The C2 and C3 bond. This is our view, the C2 and C3 bond. So in Sawhorse projection, first we are going to write that bond, C2 and C3 bond, using a line. Okay. And this line we don't write either horizontal or vertical. We are going to write a slant line, not a horizontal line or a vertical line. Or simply we have to put in this line, not a standing line or a sleeping line. Okay. See, when these kids are taught of the basic shapes, how are they taught? The vertical line is not called vertical line because vertical is a big word to them. It is called a standing line. And the horizontal line is called a sleeping line. Sometimes using those terms are handy in discussion of stereochemistry also. So this line is neither standing nor sleeping. This is written in a slant way, tilted a bit, slant. And then put the bonds which show the substituents on the second carbon atom, put the lines to show the substituents on the third carbon atom. So this will be the Sawhorse projection of butane. This is against Sawhorse projection of butane. But what is the difference? This is staggered projection. This is the eclipsed projection. Okay. Why is it staggered? You can see, right? The methyl group on the second carbon atom and the methyl group on the third carbon atom are anti-parallel in nature. One is up and the other is down. So you convert this into the Newman's projection, you will get staggered. You convert this into the Newman's projection, you will get eclipsed conformation. Okay. So this is how we write the Sawhorse projections of molecules. In fact, the Sawhorse and Newman's projection are complementary to each other. The same thing you are representing through both the conformations. They are complementary to each other. That means what do I mean by complementary to each other? They can be interconverted easily. They can be interconverted easily. Why do I say so? Okay. Anyways, so this is what I wanted to, I was explaining about. You see, if this is the molecule, you are going to have your eyesight here and viewing the molecule from the sideways along this bond. Write down the conformation. Eclipse staggered can be interconverted easily just by rotation of C2 and C3 bond. You rotate this 120 degree, a staggered will become eclipsed. And of course, eclipsed will become staggered if you rotate by 120 degree. Similarly, this is butanoic acid, where a CH3 is converted to COOH, is now COH. Butanoic acid is also there. But see, whether Newman's or staggered or even fissure, what is the first what is the care we have to take? That the carbon skeleton should be represented along like this. Okay. If this is the bond, the carbon should be represented almost in a staggered way always. You see this? Because you know staggered conformations are more stable, less energetic and more stable. So when you write the conformations of real molecules, either using Newman's or Sawhorse, try to keep the carbon substituents, not the other substituents, carbon substituents in staggered manner, not in eclipsed manner, staggered manner, because that's the most stable conformation. And you see this? This is how a Newman's projection is converted to Sawhorse. Converting Newman's projection to Sawhorse and vice versa is really easy. The same molecule, tilt it a bit and view from the sideways. You are going to get this. See here, again you are going to get. All this color coding is only to make you understand better. A circle which is green color in the Sawhorse is now a dot which is green color. A front carbon which is a dot, red dot, is a red dot even in the Sawhorse. And you see, these are the projections. In fact, in this Sawhorse projection, You have wedge and dash representations again, but not required. You can just write simple lines like this or like this. You can write simple lines also. Okay, fine. So don't worry about the wedge dash projection. You just leave it there. When we take up interconversions, we are going to do this. You just see how a sawhorse is converted to Newman's. In this example, what we did, a Newman was converted to sawhorse. Here, sawhorse is converted to Newman. Sawhorse, don't look the molecule from the side angle. You come here, have the line of viewing here. Then what happens? Your front carbon is in a dot in front. 3 hydrogens, red one attached to the front carbon. 3 hydrogens, blue one attached to the rear carbon. The rear carbon you represent by a circle. Is it not? Okay. So what I tell is that okay, fine. That the Newman's and Stagger's and Sawhorse projections can be interconverted easily. You just have to, instead of viewing it from the front, up front, tilt it like this. If the molecule is like this, tilt it and view from here. That is what the way we write projections, Newman's and Sawhorse. In fact, maybe this is a bit difficult for you at this point, but still no problem. I'll explain this. You can write the Newman's projection for cyclic alkanes also. Okay, like a cyclohexane derivative. In that case, how to write? It's a question. You may feel a bit difficult at this point, but later as you go along, you will understand better. We are going to make, if there are 6 carbon atoms in the ring, we are going to choose any 2 bonds. Let us choose this bond and this. Let us choose this CC bond and again this CC bond. You write 2 Newman's projections for along this bond as well as along this bond. So if you write 2 Newman's projection, how do you see them? Okay, fine. This is my front carbon for this Newman's projection. I have written here, and this will be my rear carbon. I have written a circle and leave some gap. Later we will connect them. Front carbon here and the rear carbon there. The substituents of the front carbon you write off. Which are the substituents? Chlorine and ethyl. You have written ethyl here. Substituents of the rear carbon. Write it. Which are the substituents of rear carbon? Methyl and amino group. Where are those methyl and amino groups? This is the methyl group and this is the amino group. Okay. Similarly, you do it for one more bond. If I don't do interconnections, if I don't show these 2 connections, then these will be 2 independent structures of independent molecules. But this is a cyclic molecule you are writing. So you have to connect them. You have to connect like this. The bonds, CC bonds, should be shown in a continuous manner because this is cyclic structure. See here, 1, 2, 3, back one is the 4, 5th carbon atom, 6th carbon atom is again the circle. Okay, so how have we written the cyclic for the Newman's projection of a cyclic molecule? 6 carbons, 2 dots, 2 circles. So that will account for 4 carbons. The other 2 remaining will as a methylene substituents, CH2 substituent. This is a CH2 group and this is a CH2 group. Is it not? But now you can ask me a question. Why don't I write my NH2 here and a methyl here? Is it not? Why don't I write my NH2 here and a methyl here? If I interchange this, does the meaning change? Even again here, why don't I write H here and OH here? That is because the stereochemistry of that is fixed by the stereochemistry of the molecule itself. How to convert them exactly from the stereochemistry point of view, we will understand later. Okay, why I can't write NH2 here and methyl here? Because you know, okay, let me explain here. Okay, fine. See, fine. We'll skip this. When I take up interconversions, I'm going to explain. This is the Newman's projection of methyl cyclohexane. You have a chair conformation. The carbon number 4 and 5 we have taken to write the Newman's projection, as well as 2 and 1. 2 and 1. The 6th and 3rd carbon we are going to write as CH2 substituents of the Newman's projection. Hydrogens everywhere, and the methyl on the first carbon. Methyl on the first carbon, that is it not? 1 here. So that should be, the methyl should have been here. The wrong structure. Methyl should have been here. H is here because this is the first carbon. The methyl is on the first carbon. So shift this methyl here and H here. So you can write the Newman's projection of cyclic molecules also. But as I know very much, I know well that when I show this as a slide for a brief time, it is really difficult to understand. The only way to this is first work with models and write down the structures yourself, and work with structures a lot. You have to solve many problems regarding interconversions of structures and writing projections. Only then you will understand better. Yeah, not now. Okay, so this is about the projections, Newman's and Sawhorse projection. So till now, how many projections have we learnt? Till now, how many projections have we learnt?